Alright, so before we start our discussion, do you have any questions for me? No questions? Alright, today we are going to discuss two things. One is how to tune and debug Spark, and then we will talk about how to do the Spark streaming with the live examples. So today's session is very important. Alright? Alright, so question from Mehdi is let me just open my notes. All right, here we go. All right, and where do we keep all of these files? Yeah, 17 October Spark. All right, so question is, what is the difference between Kafka and Flume? All right, so frankly, with respect to how do they work, there is not much of a difference. The duty of both is to take data from one side and push it to the another side. The difference is Kafka is centralized in the sense that there is a single queue for whole organization, okay, and users keep writing to it and reading from it. Okay, so Kafka is a general queue system, heavily distributed and very resilient. All right, and Flume on the other hand is a transport system in which we connect many agents together to take data together to collect data into HDFS. Okay, so if you see diagrammatically in everywhere, so let me try to display it using diagram. It's a difficult question actually. Okay, so if you think about Kafka will be like a big queue, okay, and lots of users will be writing to it, and lots of you and this data is flowing. You can imagine like it's flowing, and lots of you readers are reading from the queue. Okay, this is how any queue looks like. Let me yeah, this is how any queue looks like. All right, now if we talk about, so this is any queue. So queues are generally the new data structures like message queue, MQ, Kafka. They are built ground up. Earlier, we used to use database itself as the queue. Okay. For example, AS Oracle is a queue which is from Oracle, and it's built out of database. So they are based out of publisher subscriber model, that publishers publish the events and subscribers subscribe to the events. And generally, there is a way to differentiate between one application and another what they are writing. For example, in case of Kafka, you have many you can say topics. Okay, so you can imagine that this is related to one topic, this is related to some other topic, and so on. All right. So many people are writing with respect to many different topics. All right. So this is how a queue looks like conceptually. Now, when we think about our Flume, the diagram is little bit different. Okay. So I hope this is clear to you. Let me. How do you? Okay. All right. Now let's take another example. All right. Here, the Flume, on the other hand, okay. So if you have say 10 computers in your network, 1, 2, 3, and 4, and from these 10, let's say 4 computers, you want to gather the events in your HDFS, and let's say this is your HDFS. Okay, this is your HDFS, and these are your web server number 1. Okay, this is your web server 1. This is your web server 2, and this is your web server 3. All right, and yeah, and let's say this is your web server number 3. So everywhere the events are getting generated, and you want to take this data to HDFS. So what you do is you run Flume. Okay, so you run Flume, and on every node you install Flume agent. So Flume agent will push the data to HDFS. Okay, the the Flume agent is going to push the data from every node onto HDFS, or maybe we can configure it to deliver to another agent, and that agent would deliver here. Or maybe we can configure things like this. All right. So basically, it's a data gathering mechanism from a whole system. It's not heavily tolerant. As in case this node goes down, the event getting generated from here will not reach HDFS. Okay? Or in case this node goes down, let's say, because this node has dependencies of these two. So what will happen is the data from these two nodes will never reach HDFS. So this is how Flume looks like. So Flume is installed as here. There is one Flume agent. We install generally Flume agent everywhere. Okay, here, here. So from everywhere, the objective is to take the data to HDFS. Is it clear, Mehdi, now? All right. All right. Feel free to ask because I'm not sure if it is clear much. Okay. But so in both the cases, whether Kafka or Flume, data can be of any type. All right. So the similarities between the two is both process in real time. Okay, in real time, as in and both process in real time, and both are continuous services. Okay, both both are continuous, as in it keeps happening all the time. It's not like our usual program that you executed, it processed the data and stopped. No. In case of Spark, in case of Kafka and Flume, in both the cases, the processes keep running 24 by 7. The process will keep running 24 by 7. If any of the agents, if they don't find the data, they won't send it, but they will keep on waiting for the data. Okay? Both can produce, both can transport variety of data. All right. Now, next good question is, are there producers and consumers in Flume? Every Flume agent reads data from somewhere and writes data to somewhere. Okay? So every Flume agent reads data from somewhere and write data to somewhere. And that somewhere could be another agent. So one agent could be producer for another, and one agent could be consumer for another. Therefore, the agents itself are the consumers and the producers. While in case of uh, our usual queue, the producers are the applications in the organizations, and and the 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 consumers also are the I mean, consumers are also the how should I say? Consumers are also the applications from the organizations. Okay, so basically, while Flume collects the data, Flume is like real-time collection of data. The the queue is basically Kafka or any other queue is a little different. It basically doesn't collect the data from all the places. It basically receives the data on one hand and hands over to all the other people who are listening. Okay, and uh, and that's how it works. All right. Although it's little confusing to look at it. Okay. The All right. Now, sometimes what you need is there is on one hand, let's say your Flume agents are there, Flume agents, okay, are preparing data and putting it into HDFS directory. Okay, from there the data could go to Kafka, and then to various, after processing, goes to the goal after. So here the processing engine will be yours, and then after reading the data from Kafka, it will you know, so it'll give to other listeners. All right, this is how it works. So while Flume gathers the data at one place, you can use Kafka to read data from that place and give it for processing. Okay, we will, as we'll discuss further today, and we'll try to demonstrate few examples of Kafka in real time. Using Kafka, you can read. Okay, so using Kafka, or maybe directly stream processing from here. From here, you can also directly go for processing using Spark or Storm, and basically process file by file in Spark. All right. Few more things to note here. The As I told you that while Kafka or Spark, Kafka promotes a lot of processing during the translation, because Kafka's sole objective is to get the processing done, right? Okay. Kafka provides a strong mechanism to process, while process as in the receiver will receive the data and will process the data, okay, while Flume doesn't. Okay, if you need any processing, you would write you would write custom agent. Make sense? So as a thumb rule, you can think of Flume as really fast-paced transport system, real-time transport system. As and when data is getting produced, Flume is pushing it to the final consumer. Okay, that is the objective of Flume. While in case of Kafka, it is, on one hand, Kafka is from receiving events from many applications in organization. Okay, and on other hand, lots of users are listening to it. Similarly, Kafka is centralized, as in there is a single machine or a single quorum running, which is discoverable and addressable, while that's not true in case of Flume. Wow, that was an interesting question that made me think. That made me think exactly what is the difference. I think I would write a bigger blog post for this. All right, all right. Uh, Here is Ishwar's question. Question is, which one is faster? Okay, which one is faster? Very difficult to say, honestly. Okay, so all right. So honestly, I have not done a good benchmark on the two. Okay, and the benchmarking will itself need to be thought through. Okay, I need to figure this out. All right, but we will show you that today. All right. So, so my estimations say that the the Kafka or Flume, they're okay. So we could test it actually. Let me. All right. Both are pretty fast, as in Flume is designed to carry the data in really fast manner. All right. So that is a little bit about Kafka and Flume. All right. Good. I'm happy, Ishwar, that you have worked on Kafka. Then my life is going to be a little easier. And in case we get stuck somewhere, we can ask you. All right. Great. All right. So we will uh, carry on with our usual discussion of Spark, and then so today's agenda, I'll be very clear. Today's agenda is to understand how to fine tune Spark, and what are the parameters, and then we will get into Kafka, and I mean not really Kafka, but Spark streaming. We will do two examples on Spark streaming, one using Kafka and other using the usual tools. Okay. All right. So one will be using Kafka and other will be using normal TCP layer. Just like if you have attended my Flume, we had in the usual TCP connectivity. Similarly here, on one port we will be writing to it. From the same port, it will be reading and will be processing the data. That will be after we finish the tuning. Alright, any questions before we jump on to this? Gaurav, Jitendra, Mehndi, any questions before we move on? Yes? Alright. Jitendra, any questions? Alright. Alright. So, okay, so when we were configuring our Spark, there are two ways to do it. One is providing various configuration parameter in the arguments, and this is good, as in one is you can provide all kinds of arguments, configuration parameters in the argument to our Spark submit. Okay, while I mean, if you are writing a program and you want to control it more, you can create a configuration object like conf, and then set various properties to conf, and then create your own the Spark context. Okay, you can see this here. So both mechanisms are good, just that the first mechanism is for really custom development of product, while second mechanism is more popular because here the configuration is being hard coded. Unless inside your program you are reading configuration from your own configuration file, or are computing the configuration, the first one is not really appreciated, while the second one is what we generally appreciate. All right, where we can pass most of these arguments on the command line. All right, so these are the two ways to tune your application. So you can control a lot of behavior of your application using these properties. All right, let me just do a quick recap on to what all properties are there. All right, so all right, so we have mentioned two things here, one in the bracket, one is normal. Okay, and the normal one is set through conf.set, while this is the command line argument. So first command line argument is spark.executor.memory. Okay, that controls how much memory to use per executor process. Okay, so how much memory is going to be consumed from every executor, and this memory has to be lesser than or equal to the one allotted by your resource manager. Okay, so since every executor is going to be executed inside a resource manager could be mesos, or resource manager could be yarn, or it could be standalone of Spark. All right, so you can control how much memory each executor is going to consume. By default, it's 512 MB. In case your yarn cluster does not, yarn cluster consumes lesser memory, has provided lesser memory for each node, then you have to bring it down. All right. Okay. So that is another. So now how many cores each executor has? Okay, or you can say that how many threads are going to be executed inside each executor, because while Spark will be running its program on each node, how many instances of the program need to be run on the same machine? That will be governed by how many cores do you have on each node. Okay, creating lot of threads will not make any sense unless there are number of cores available on any of the machine. Okay, so creating many threads will not make any sense unless you have multiple cores available or multiple computers available. Next is how many maximum. Okay, how many maximum? By default there is no limit. Okay, so you can also limit that sometimes. Gaurav's question is executor equals to Spark worker node? Yes. So executor as in the real execution, real thread or real process being going to be executed inside Spark, inside the Spark. All right. So, or you can say Spark worker. Okay. Yeah, you're right. All right. Moving ahead. So sometimes what you want to do is even if as we told you earlier, right, when we were discussing the what happens in case of in case we are doing the accumulators inside our transformations. Accumulator says we are accumulating data inside the transformation logic such as map and flat map and others. So in those cases, what was happening we discussed earlier is, what if there is an speculative execution? Okay, let me describe the process again. So in case of speculative execution is, let us say there are three nodes out of which one is very very slow. Okay, so Spark or even Hadoop does this. Spark would run this slowest program, or whatever work has been given to the slowest node on some other third node. Okay, so the moment it realizes that one of the node is very slow, or it gave the work to three, out of that one has already finished, two are still running. Out of two, the slowest one, it will give it to somebody else. Okay, if that somebody finishes the work, that will be taken into account, and this one will be stopped as soon as the work is finished. So it's like, if you suspect that one of the worker is really really slow, you give the same work to somebody else. Now whosoever finishes first will be considered for the output. All right, so that is called speculative execution. So you can turn it on, it becomes really really greedy, as in the same work will be done multiple times by multiple node, only one will be considered. Okay, all right. So whenever you cannot take you want a really really fast processing. Okay, then you generally turn Spark speculation. Okay, it consumes more resources, but it gets the work done in a comparatively faster manner. All right, by default speculation is off. Also you can specify, okay, the timeout interval for the block manager. It's an internal timeout used for tracking the liveliness for executor. Okay, for for jobs that have long garbage collection pauses. Okay, tuning it to be 100 seconds or higher can prevent thrashing. Okay, next is the some, if you have some more Java options, like when have you run Java jar, when you run your Java program, you can provide a lot of options on the command line. And in case you have some more options, you can pass them here. Okay, one such option could be for the real-time debugging. Okay, so the real-time debugging options can be passed via these extra options. Okay, if you want more class path, if you want more library, you can pass all of this here. Okay, say for example, uh, related to GC, you want to say that once as the Java virtual machine crashes, save the data here. So those kind of options you can provide to JVM using these variables. All right. So you can control, because at the end of day, I'll be very clear. I think some people still have doubt that at the end of day, Spark is running in Java. Okay, Spark is a Java process that runs whether running on Mesos or whether running on Yarn, it's a Java process. Internally, it's a Java process. The Scala is getting converted into Java, while Python is getting executed by Java program. So under the hood, in the real-time interaction, it's basically Java. All right. So what are the components of execution in Spark? Before we go into optimization, we need to understand these basic units, because there are many cases you will realize that the whole optimization or tuning is all about understanding your process and optimizing them, figuring out what went wrong in my program. And for that, you need to understand what is a job, what is a task, and what is a stage. All right. All right. Let's do a walkthrough. Let's do a walkthrough here. All right. Let me first give you a quick overview. What exactly is a job? The whole word count problem is a job. We say that here is my program. It does a lot of things. Okay, it runs one map, another map, and some other map is here. Then we figure out what are the individual tasks. Okay, and these tasks are running one transformation, running an action, and so on. And then there are stages. So multiple tasks are combined into stages. Like all the maps, if they are occurring concurrently, will be combined together and they will be named as a stage. All right. Now here let's see what's going on. So in the first line, you are creating an RDD. RDD equals to the spark context dot text file and then this file input. Now this spark context can either be, if you are in interactive mode, you get this SC pre-cooked. Okay, even in the interactive mode you can pass on all of the arguments which we have discussed earlier. Okay, and if you are running in a program mode, as in you are submitting an application, in those cases, the SC will be Spark context will be created by you by passing the configuration object, the way as shown in this. So here you will have to import SparkConf and Spark context, create an empty object of SparkConf, and then we set various parameters to the conf, and then we create, this is creation of object in Python. Okay, then we create a Spark context on the basis of this conf. All right, and then we can continue. So whenever we are launching PySpark, the interactive interface, these are the things happening in the background. All right, so let's go through this go through these steps. First one is RAD equals to sc.text file. This is the step where we load the data. We prepare RDD. And what does it mean by preparing RDD? First is discovering what mechanism are we going to use for reading this file. There are two ways to do it. One, two steps in figuring out where is my data coming from. Okay, one is this method. Here this method says the data we are loading is a text file, and this text file could be anywhere. It could be on the local file system, it could be in HDFS, it could be in S3, it could be elsewhere. That part, where exactly is this, is governed by the protocol here. If we say file colon slash slash, that means it will think it's a local file. and on all the worker nodes, it will expect the file on the in exactly at the same location. So the file colon slash slash is good for network file systems, while HDFS is good for in general if you have Hadoop file system already. Now, so when it loads the data, it basically does a mapping. It basically does a mapping between actual actual lines of file and the newly created RDD. And RDD is there are multiple things an RDD is. Okay, first, an RDD is an kind of an array representation of pointers. An RDD is array representation of pointers. It basically is a big array. An RDD is generally an array of pointers, each pointer pointing to the exact data. Where is it? Second part about RDD is RDD has something called parents. Parents means who is the parent of this RDD? Where is this data going to be? Alright, so RDD as such is not a data store. RDD does not load everything into the memory right away. Okay, unless we do a persist. Alright, now, so when we say RDD.to debug a string, it will tell us clearly what is it that we are looking for. Okay, what is it that this RDD means to us? Okay, you can try this. All right. So let me try to also we are setting up our new we are setting up our new CloudX lab. All right. All right. So this is on H1, H2, H3. So we can open the web console and copy this. All right. So I will just send it to you as well. All right. I will send it to you in the chat. Okay, so I've sent you the login / password. You can also open up any of the terminals. All right. So it's H1. You can see h1.cloudxlab.com, or you could use H2, or you could use H3. All right. All right. So probably by in couple of days you will have new ways in which you will have your personal login. All right, you'll have your personal login automatically created. And the reason why we have created a new CloudX lab is first, we have upgraded the version of Hadoop. You can see Hadoop minus version. Okay, this is 2.7. And also in this, you have on 8080, if you log in with the same credentials, you will see more details. All right. So this is, you can see Spark, Kafka, everything has been installed for our this thing, and all of this experimentation, this installation has happened through Ambari. You can have a look on how to install HDP, which is Hot and Work Data Platform, using Ambari. All right. It's very straightforward. You just need to make one thing called Ambari agent, and rest of the things as Ambari server. One node you will make Ambari server, and this is Ambari server, and rest you will mark as Ambari agent, and then you will go into hosts, and here there will be a button called add hosts, and you can start adding as many hosts as you want. All right, it's very straightforward. You can give it a shot. All right. So again, so this was a quick overview of this cloud app. Now coming back to your questions. All right. So there is a question from Mehndi. Let me finish this discussion and then we will take up your question. All right. Now next is one is that RDD is here represented by the data loaded from a file, and then we can let's just try to demonstrate. All right, here we have to go with our usual. All right, here. So I've added my bin folder here in the path. Okay, and then I'm running PySpark. This is the older one, not the newer one. All right. For streaming, we'll use the newer services because the data for our normal work is still in the older one, older Cloud Labs. Okay, so if you say rdd dot to debug string, okay, so it shows you the details about your RDD. Okay, so it says that total input paths to process is 1, and okay, and similarly it is the map partition RDD at a text file using this particular method, and the actual file location is here. All right, and so on. So you can see that, and when we go further, when we go further and we say that because by default this is going to be an RDD containing an array of lines, a RDD where each object is a line from the text file. Now we can convert that into one word per element by doing the flat map. All right. Now here you can see two debug strings. When I say that, it shows you that now this time words is a Python RDD. Okay. All right. So basically, words does not contain the data yet. Words is a representation. Words is the representation of this RDD, which says that words will be prepared by first computing this RDD and then doing the flat map. All right. Now words. Now the third RDD called words KV is equals to this. And again, if we say, it shows that words KV is a Python RDD, okay, and which is Python RDD, okay, which has been computed from a mapped RDD, which is from a text file. All right. Now, when we say things like this, the moment we say reduce by key, okay, it is producing a newer RDD. Now let's have a look at what goes inside this. Now here you can see that the, it's another RDD and another partition RDD, and it's being produced by pairwise RDD. You can see, all right. There were map partitions, then there is pairwise RDD. So basically an RDD, this results is keeping track of all the parents it has. Okay, so result is being produced by this function called reduce by key on something which was produced by map, okay, and on something which is produced by flat map, on something which is produced by text file. So this is what an RDD typically is. It's a graph of all the dependencies. All right, it's a graph of all the dependencies. So the moment when we say results dot an action, when I say results dot count, okay, or results dot count, then the processing has started. Now you can see that it has started all kinds of processing. Till now, our results were just like when you execute ant build, the way you execute ant build, and everything gets computed. Similarly, but before that, before you run ant build, it's everything is just a task, just a declaration. Similarly here, till the point we had typed results.count, everything, all the RDD were just steps, were just one task. It was just a declaration. All right. So the moment you say you execute an action, the whole process has started. It has started reading the data from Hadoop using two different, because this data has got two input splits. So it has created by default two tasks. It creates one task per block. All right. And it has taken this much time to do the computation. You can see that. All right. So this is what goes on behind the screen when you run a Spark program. All right. So on one hand you have this RDD graph. So on one hand you have your plan, and then that gets converted into stages. Okay. So we started with reading Hadoop RDD. Then we created, by using text file, we created a mapped RDD. After that we run a map, then we ran a filter, and then we run a reduce by key. Okay. Now if you look at it closely, all of these things like loading the data, running the map, filter can be done on the same node where the data or blocks of data is there. Therefore, all of these will be combined together into a single stage. before execution. All right. So all of these tasks, map, filter, text file, all of these will be combined together into a single stage. Right. So this is the physical plan, and this is the physical plan on the right hand side, and with various stages. It has got two stages. While on the left hand side, our job had all these things mentioned in it. Okay, all these commands mentioned in it, which got translated into tasks, individual tasks, and those tasks got combined together to form stages. All right. So Mehdi's question is, how RDD processes streams of data while parent RDD never update? Okay, so we don't need to update the parent RDD. Parent RDD is nothing but a representation. Parent RDD is not data. Parent RDD is just a command. So when we say RDD, when we say streaming on RDD, we will consider it later again when we are discussing streaming, and we will talk about more details that time. All right. Should I move on? All right. So each task internally performs the same steps, such as fetching its input either from data storage or an existing RDD, or using shuffle outputs. Okay. Then performing the operation necessary to compute RDD that it represents. For instance, executing filter or map, or writing output. So either your RDD is because of reading some data from somewhere, or your RDD is because of some translation, okay, or your RDD is writing some data to the output. So it does almost these operations internally. So when you think about an RDD, if you had to build an object diagram of RDD, it'll look like this. So basic RDD, okay. There is some basic RDD providing us map function and various kinds of functions. Okay. Now there is one RDD called file loader RDD, which extends basic RDD and so on. And file writer, okay, or it would be or it could be another one, could be some action, what do you call, transformation, okay, which also extends same thing. Now these are the three things which an RDD does. These are the three things which an RDD does. So there could be three forms of RDD internally, but for an end user, it's the same thing. All right. Again, whatever I have discussed till now. So user code defines a directed acyclic graph. When we are coding, just like in Pig, we are basically creating a DAG, creating a directed acyclic graph. All right. So operations on RDDs create new RDDs that refer to their parents and thereby creating a graph. All right. So you can think of it. I mean, just like your Maven and or maybe your project plan. Everything is a directed acyclic graph. Whenever you do an action and depends on other actions which depend on other actions, then if you draw such kind of scenario, you will find out that it is a directed acyclic graph. Because it is directed, one has to finish before the other. It is very clear. And a cyclic, it should not be cyclic in the sense that one task should not have a dependency to itself. If task 1 depends on task 2 and task 2 depends on task 1, it will never done. Therefore, it is a cyclic without cycles. Actions force translation of DAG to an execution plan. So the moment when we say when we say collect or when we say take, that is an action and that forces the whole DAG to be evaluated into an execution plan. When you call an action on an RDD, it must be computed. This requires computing its parent RDD as well. So in this case, it doesn't have this RDD doesn't have a parent RDD, while this one has a parent RDD. Okay. Okay. So the job will have one or more stages, which are parallel waves of computation composed of tasks. Okay. So the out of uh, stages are built out of multiple tasks together. Okay. And each stage can have one or more RDDs in the DAG. All right. And once you are done with execution plan, next is executing the stages, executing the tasks on the cluster. So stages are processed in order with individual tasks launching to compute segments of RDD. Once the final stage is finished in the job, the action is completed. All right. Now, how do you find an information? Let's say you are running something and something goes wrong. How do you find what has gone wrong? All right. If you have to find out, you have to look at two places. One is Spark Web UI, which always runs on the 4040 port by default. Okay. Since we are running one of this one basically, where is my terminal? I think probably one of you are running this. Alright, so it shows you the jobs, stages, and storages. Okay, alright, and also please note that when we'll run our streaming, you will see one more tab here called streaming. Okay, alright, or you could have a look at the log files produced. So the first tab in case of Spark is where is the is this running on Hadoop? So it says that it has started the Spark UI at this port. All right, you can see that. So jobs generally list what's going on in any execution. All right. Job generally, let's just try to execute something and it will show you. This is our RDD. Then we created words. Then we created key value pairs. And then we did the count. And then we did the result dot count. All right. So you can see here that there is a job running in the background. See that? Yeah. So it has got two stages, stage 0 and stage 1. First, we do the count and then we do the reduce by key. Sorry, first we will do the reduce by key and then we'll do the count. Alright. So under each stage, these are the various tasks. So details for stage number stage 0 are these. It has got these many tasks. Alright. You can also have a look at the DAG visualization if that makes sense to you. Alright. And this is the timeline of execution. So driver started at this point and then this is idle time, I think. Alright. So using this UI, you can dig into the behavior of your jobs. Okay. And also you can have a look at what are the storages, as in if you try to persist the data, then that will be in that will reflect here generally. Okay, right now for some reason it's not reflecting, but it would reflect. All right. So all right, the also please note here that the moment we say persist, okay, the behavior of RDD changes. It instead of evaluating the parent, it will start evaluating only the value which it has stored just now. When we say persist, it basically computes all the dependency and then store that locally. Okay, so that when again and again if the requests are coming for the same data, there is no need of evaluating all the dependencies or all the dependent RDDs. All right, so I hope that is clear. So first tab is job, second is stages. It shows you the clear stages of every time, and third one is your storage. It's the information for RDD that are persisted and exactly what fraction of each RDD is cached and how much. Alright. Executors, a list of executors present in the application. Alright. Application has expected amount of resources. Okay. So whenever you have to find out if the things are fine with your cluster and if it is running fine, you should generally have a look at executors in the Spark Web UI. Alright. The third is the environment. Okay. So if you want to know exactly which path, which JVM and which Java is it using, you generally should have a look at the environment. You see that? We are using OpenJDK 1.7. Alright. This is the IP address of the host that is running our PySpark, and this is the folder name where external output data will be parsed temporarily, and this is the file system URL and so on. All right. Here is the class path, and all the details about the current state of this Spark. You can see it here. Please note that if you close the terminal, it will no longer work. All right. So if you close the terminal, this will not be valid anymore. All right. So the first part where to find the information is through the UI provided by Spark. The second is to find the logs. Where do we find the logs? Okay, since it's getting executed by Yarn or Mesos or any other executor, the those resource manager have their own place to store the logs. Okay, you can always go to what do you call 8088. So all right, so in Hadoop, this is where everything runs. This is where everything this is a at 8088 port. You will see all the details about all the applications in this cluster. Okay, so if you are running your Spark application inside the cluster, that information, as in what exactly is happening to the application in the cluster, it will appear here. Okay, so this will also be there even if you are running in the cluster on Yarn, and this will also be there when you are running in the on the Yarn. Let's try to execute this. Not this one. All right, we have already done that already. Okay, so if you run any of the Spark programs, it would appear here also. Let me see if it is there. Now you can see that this is an older run. When we try to run it, it shows clearly that its name is Pi Spark shell, and it's getting executed inside Hadoop. And if you and this being executed on Hadoop 4, and if you go into more details into logs, it will show you all the logs. Just wait for a minute. Yeah, these are the logs available in case of the resource manager. And who is the resource manager for right now? In this case, the resource manager is Yarn. It shows you all what exactly had happened. All right. So So in case of Spark standalone, because Spark can run in multiple manners. One is standalone, as in it doesn't require resource manager. It can itself have its own executors and can delegate the work. And without even, if you don't have Mesos or Yarn, it can do it by itself. So application logs are directly displayed in the web UI, which we have just shown. They are also stored by default in the work directory of Spark distribution on each worker. In Mesos, the logs are stored in work directory in Mesos slaves, every slave, and accessible from Mesos master UI. Although in case of Yarn, I showed you there is an interface to check in case you want to do it from the command, you can do that. Okay, you can just take the application ID from here. You can just take the application ID from here and run this command called yarn log application ID. Okay, you can run yarn log and right. It shows you all the logs. You see that? It will gather all the logs from all the nodes and then it will display to you all the logs for an application ID. Alright. So we talked about two things to find out information. One is the web UI, other is the logs. For logs, either you could go to 8088 or h1.cloudxlab or hadoop1.nobigdata colon 8088. or you could run the command called yarn. All right. So the key performance considerations for fine tuning is, first is level of parallelism. How many machines do you want? Second is the serialization format, in meaning in which format do you want to store the data. Third is memory management, as in how do you want to cache your data, or how much data do you want to be cached. And fourth is what kind of hardware do you want. So these are the key performance consideration. All right. Now, since we have our ideas clear, so what we know right now, we understand how does an RDD get computed. Second, we know in case of running it, where do we find information about it. One is UI, other is logs. Okay. And this logs UI is the URL is also given out by 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 Spark to you when you run an action. It will show you this is the URL on Spark on Yarn cluster where you can track the progress of your job. All right. Now, first that was one thing, and now the real performance considerations. So, what are the considerations that you will do to in order to figure out what exactly in order to optimize your cluster. So let's jump in. All right. So this is very interesting. So whenever we load data into our Spark, whenever we create an RDD from either by using text file or by using sc.parallelize or by using Hadoop API. So howsoever, when we load data into Spark, how many partitions are created? That defines the parallelism. More number of partitions sometimes would result in better, sometimes it result in worse. Okay, so by default, it creates a single task per partition. The partition is generally governed by the data. Okay, if we are loading the data from HDFS, it will automatically create those many partitions which are equal to the number of blocks. If a file is having 20 blocks, then there will be 20 partitions. Okay, and also please note that whenever we are executing these, the execution will happen near the data. Okay, that part when we run our map function on particular on an RDD, this map function will be taken to the node where that section of RDD is located on the same node, and then it will get executed, or it will try to do it on the same node, and if that node is which contains that portion of RDD is busy, then the work will be given to somebody else. All right, so that's how it is. So that's why, so the partitions are generally decided by default by which file are you reading, and you can also control number of partitions. So if you had noticed that sc.parallelize or sc.text file has one more option which you can pass as second argument. You can say comma 20. That means we are trying to create 20 partitions out of the input data. All right. Now, by default, there will be one task per partition. Okay. So if you have 20 partition, there will be 20 tasks and a single core in the cluster to execute. So a single core, a single task on every partition. As in, if you have 20 partition and you have 20 machine, then only one core of those machine will be dedicated to it, and then there will be a single task per partition. All right. Now, by default, a good degree of parallelism is based on the underlying storage. In case of SDFS RDDs, when you're preparing SDFS RDD, the the partition is one partition per block. All right. Now, if you create too few partition, if there are too few partition, what will happen is there'll be too much of work on one node. Okay. So, and in case you start creating more and more partitions, what will happen is more and more partition, then there'll be a lot of overhead, because there's a cost associated with maintaining with maintaining the partitions, with doing operations on partitions, as well as in the transport. Therefore, if you have too too many too many partitions, then it'll be a humongous overhead. Now, how do you control parallelism? How do you control how many partitions are going to be there? One is, while loading the data itself, you could tell and force it to create that many partitions. Okay. Next is the most of the shuffling operations accept a degree of partitions. Whenever we say reduce, you can mark how many partition do you want. So whenever you say sort, it will you can also specify how many partition do you want. So any reshuffling operations will take an argument for repartitioning. Okay. Or you can forcefully create repartition of your data by saying my RDD dot repartition. Okay. That is for two, and sometimes this repartition not only expand your RDD to more nodes, but it can also shrink the total RDD into fewer number of partition. So repartition, as the name says, is for repartitioning the RDD. Now sometimes when you are shrinking your RDD, it makes a lot of sense to use coalesce over repartition. Coalesce is better than the repartitioning. Less. Okay. Now, when do you need to shrink the data? When do you need to use coils? All right. So imagine this. Imagine this, that we are reading data from S3, and the filter operation is likely to leave only few elements in the full RDD. Let's say there is a gigabytes of data in the input RDD. There are many partitions in the input RDD which is loaded from S3. Now, when you run filter on this RDD which is having so many partitions, you know that there will be only very few records that will be left after filter. By default, the result of filter will will have those many elements, just that some of the elements will be missing, or most of the elements will be missing, but total number of partitions will remain the same. After filter, no matter how many output elements are there, the sorry no matter whether there are only few elements or many elements left after filter, the total number of partitions will remain same. That means most of the partitions will be fairly empty. All right. Which means whenever we run something, even though the data is very small, it is unnecessary overhead of dealing with so many partitions. Therefore, it makes sense to coalesce the RDD to shrink it into smaller partitions. I'll show you this with a small data, but that would be sufficient for this. So, all right, let's try to do things. Let's try to do things. I think that's a better way. First, I'll try to first I will try to filter a huge amount of data, and then after filtering, I'll count number of number of partitions, and then after the counting the number of partitions, we will try to coalesce and then compute. I'll show you that. Okay. Now have a look at this. This is an example. It shows that we loaded the data from text file from S3. You can see that instead of HDFS, we are using S3. S3 is Amazon's storage for files. Once we load it from there, we said get number of partitions, and it gives us 35,154. Now, when we say filter and we are only interested in lines which are of 17th October 2014. Now, if you say lines dot get number of partition, it will still say the same number of records as it were before the filter. You can see that before the filter, the total number of records were 35,000, while exactly the same number is still after the filter. Okay. And number of records, though number of partition, not number of records, these are number of partitions. Though the number of partitions is same, most of the partitions are empty because most of the elements are removed. Now, if you coalesce, coalesce the RDD, it will suddenly shrink, and then you can cache it afterwards. That is up to you. And if you force it to bring it into small sections, it will bring it, and then you can see that lines dot get number of partitions, it will show you total number of partition is 4. This has happened because of coalescing. All right, let's try to check if it does really help or not. Let's say all right, so we loaded the data. Next, let's check total number of partition in this RDD. By default, there are only 2. Okay. Next, let's just filter out all the lines. Just keep only the lines which start with this. So for that, we are saying rdd.filter. We are passing an anonymous function which first converts the line into lower and then checks whether it starts with this or not. Okay. Now, even after filtering, the total number of partition will remain same. Okay, now let's have a look at how much time does it take. It took around 1.4 seconds. See that? It took around 1.4 seconds. Now, if we do the same thing, but this time we do the coalesce. Okay. All right. Let's try to change the order. Yeah. Let's try to coalesce and count. All right. And then again count. Now you see that it has taken only 964 milliseconds to compute. All right. No, it has taken one second to complete. Earlier it was 1.4. Earlier it was 1.4. Now it is 1. You can see the difference of 50%. That is because we have shrunk our RDD because it is mostly vacant. It is similar to when we say coalesce, it is similar to what do you call defragment. Okay, it is equivalent of defragmenting. All right. Now the second thing that you can control is the serialize. So first one was that you do the repartition. Okay. All right. So first point we discussed about parallelism, where we tried to repartition. Second part of the discussion is the serialization format. That is another knob with which we can with which we can control the performance of our Spark application. So what is serialization? While transferring or saving objects, we need serialization. And for shuffling operation, whenever we are doing shuffling operations, of course, when we are ordering an RDD, the elements have to be reorganized. At this point of time, when elements are being reorganized inside an RDD, some of the elements will be taken out from this RDD and moved to another. Okay, what does it mean? It means that the object will have to be converted into a serialized format and then sent elsewhere into another partition. By default, Spark uses Java's built-in serializer, which is very inefficient. You should generally have a look at this. There is a serializer called Cryo, and there is a serializer called Protocol Buffer. You can use either one. All right. So Cryo is a serialization format. Okay. Spark supports the use of Cryo very well. It's faster and more compact, but it cannot serialize out of the box. What does it mean? You still need to implement an interface called serialized. Okay, serializable, just like Java program. So every class which is extending a parent object called serializable can be used with Cryo. All right. So almost all applications would benefit from shifting to Cryo because it is faster and more compact. To use Spark Serializer, you just have to set spark.serializer to this property. In the conf, you have to say conf.set spark.serializer equal to this. Alright. For best performance, register classes with Cryo. Sometimes whenever you are running an application that requires a tremendous amount of number of machines or lot of shuffling, then register the classes with Cryo. You can say cryoutils.register classes and give the jar name. It will basically make a note of all the classes who depend on this particular library. Okay. Also, classes need to implement Java serializable interface. It does not matter in case of Python because Python will anyway in Python your library will convert the file into a byte array. All right. The third is memory management part. So first was repartitioning and shuffling. Second was choosing a faster. So in our Python case, we will generally go for protocol buffer so that we can convert our objects into string. And then we'll just store that string into the disk or anywhere. All right. Third is memory management. Okay. So as we had already talked about, when we call persist, the data get persisted into the memory. There are limitations on all end here. All right. Should we take a break for 10 minutes? Gaurav Jitendra Iswar. All right, let's take a break. All right, so I'm back. Is everybody back? Should we start now? Yes? Can we start now? All right. Ishwar, let me know when can we start. Ishwar is not available for 2 minutes. All right. Do you have any questions before we start? By the time Ishwar is joining, we can you know. So today, let me just talk about what things we have. One is like how do you control the configuration spark for the performance. Second, we talked about the overall execution plan again. And then we talked about how to find information. And then we talked about the 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 key performance consideration, starting with what level of parallelism should we have, or what serialization format should we have. Okay, and all right. So with respect to serialization format is something which you want to discuss. All right. So yeah, in case of serialization format, we talked about using cryo, and based on this, it shows clearly over in benchmark. You can see that there's cryo. All right. We'll wait for Ishwar. Can we start now? All right, great. Thank you, Ishwar. So, all right. So out of this, you can see clearly that protocol buffer, thrift, and cryo comparison, you can actually go to this particular benchmark that's newer. Okay. So there are more and more protocol comparisons in this. All right. There are more and more. I think there will be KRY. Oh, so it's still one of the fastest. Okay, it's still one of the fastest. Okay, so protocol buffer is winning over cryo. So you can use protocol buffer over cryo, and then you can save the data. All right. So either cryo or protocol buffer, the time difference is not much. Okay, and we have already discussed how does a protocol buffer looks like, so you can utilize that. Next is because if you just change the serialization format itself, it will suddenly give you a great boost of maybe 200%. All right, because the default serialization is very bad in Spark. All right, so whenever you call a method called persist, it will persist the data in memory, and this memory will be some fraction of total JVM memory. By default, it is 60%. You can change that by a configuration property called spark.storage.memory fraction. Okay. So by default, whenever you are saying my RDD.persist, it's going to be in the memory. Okay. And how much memory, that's the first question people ask, that how much memory is available to it. The simple answer is 60%. Can we increase it? Yes, by changing this particular configuration parameter called spark.storage.memory fraction. All right. Now here is the resilient part. In case you try to persist and there is not sufficient memory available, so what will it do is for some of the partitions of the RDD, it will not persist the data. And which ones? The ones where the ones which are older partitions. Okay, older partitions will be deleted from the memory. The partitions which we had been existing for quite some time will be removed from the memory. Okay, which means every time you will do the computation, these partitions are going to be recomputed from their parent. Okay, so when we say dropped or deleted from the memory, here they will be recomputed. They are not cached. So in case you want more RDD storage, then you can increase it by changing memory fraction, or it's better to sometimes use memory and disk. Okay, memory and disk, meaning in case it doesn't fit into memory, it will put it on the disk, which is good enough. Next is shuffle and aggregation buffers. Sometimes, whenever you are shuffling, if there is a shuffling involved, and when does shuffling happen? Whenever there is a sorting, whenever you are joining data, or basically whenever there is a movement of data due to sorting, there will be these temporary buffers. Okay, these temporary buffers consume the memory, and how much of the memory should go to these temporary buffers is something you can control. By default, 20% of the total available memory is kept for this temporary for these temporary variables. Okay, for shuffling and aggregation buffers. You can change it by again saying spark.shuffle.memory fraction to something. Okay. Now third is whenever, I mean, this is a common thing. Whenever you run a program, you have one memory allocated for objects, other memory allocated for users code, and third memory allocated to normal variables. Now the third part called user code. Whenever you are creating a function, the way we created lambda function, we created other functions, all of these functions are going to go on the cluster. And when they go on the cluster, on every node, they are going to consume certain amount of memory. And that memory goes away from the user code section of the total memory. Okay. So by default, you 20% of the memory is dedicated to the user code. And sometimes your user code might be referring to external variables. So say you are giving a function to your map, rdd.map, and that function is referring to a global object. So that whole object will be transferred along with the function to the node, and this will consume the memory. All right. Third is hardware provisioning. So we can optimize the performance by first tuning parallelism, how many, second by serialization, improving serialization, third is by memory management properly, and fourth is by using hardware provisioning. All right. Now so whenever you're talking about hardware resources you give to Spark, Hardware, just like with any computation, will have a significant impact. The main parameter on which you should evaluate the hardware: amount of memory given to each executor, total number of cores given to each executor, total number of executors, and total number of disks for immediate intermediate shuffling data. Okay, number of intermediate shuffling. Okay, so number of disk for intermediate data. Whenever shuffling happens, if the disk is not available or memory is not available, the whole process gets impacted. This can be controlled by marking spark underscore local underscore directory variable properly. Okay. Now you can also, all right. So once you have proper memory, you will be able to set it using the executor memory. All right. Generally, an application benefits from total number of memory you buy or total number of CPUs your computer has. Okay, that's a generally speaking. Now, since Spark and most of these components scale linearly, they benefit to they run to twice as fast by adding twice number of resources. Okay, so by adding twice number of resources, they run twice as fast. All right. Now, sometimes when you start buying hundreds of gigabytes of RAM, its performance will be impacted badly because garbage collector will cause the pauses. As in, have you ever used Java? And when you have a lot of memory, the garbage collector of Java has to continuously go through that memory and clean up the objects which are no longer in use. So if you have a huge heap size of 100 gigabyte or so, or above 64 gigabyte, this cleanup will take a lot of time. And when the garbage collector runs, everything else is halted. And therefore, if your RAM is really huge, it hurts the garbage collector of Java. So it's always advisable to keep your RAM size up to 64 gigabyte or lesser. All right. So Ishwar's question is there a way to stop the GC pauses? You can only request garbage collector. You cannot stop it. Okay. Garbage collector in itself is very autonomous. You can only delay it, or even you cannot ask garbage collector to execute. You cannot force it. So in any way, so you'll have to rely on garbage collector itself. But there would be a variable which you can pass by saying minus x, and it should be available. I'll have to look at it. Good. So this was how do you tune your cluster. All right. Now moving on to the next session. All right. Any questions on? All right. So in my opinion, my strong advice to you. All right. Let me just check with you. So here is a question for all of you. You have two machines. A, okay. A cost is say 2 lakh. Memory, or let's say cost is 4 lakh. Memory 96 gigabyte. Cores are 16. and disk is 4 TB. All right. Cost. Now there is another machine called B where you have memory 48, cores 8, and terabyte. This is 2 TB. All right. Now, if you have 4 lakh rupees, or if you have say 8 lakh budget, which machines will you acquire? Mehdi says B, and Iswar says A. Anybody else? Gaurav, Jitender. So have you done any purchasing of the hardware earlier? Did you build your own machine or something earlier? All right. Iswar had changed the his point of view to B. All right. Anybody? So Jitender says B. It'll require 2 into 3. Why 2 into 3? It'll be 2 into 4, right? All right. I was hoping for somebody to say 4, 1A and 2B. All right. Never mind. So yes, it makes sense to buy 4B rather than rather than 2A. All right. It makes sense to buy 4 into B. Reason being, first, if you go beyond a certain amount of memory, like we were talking just now, that if the RAM memory goes beyond 64 GB, you get hurt because of garbage collector. All right. Now, my first point is that GC hurts in 96 GB. That is first point. Second point, this is very important to all of you because I'm recently, consulting with few people, and they are having the same psyche. So it's very important to notice here. So, so garbage collector hurts in at uh, at 96 GB. Second is the the read speed from, okay, so I'll say 2 into A versus B. Read speed from, let me, option 1 is 2 into A, and option 2 is 4 into B. So, all right, and yeah. So the read speed of option 2 is would be would be equal to twice of of option 1. RAM read speed. Okay, when I say read speed, so the amount of memory you will be able to read at the same time is also double in the option number 2, because there are 4 RAMs parallelly and therefore the read speed is doubled. All right. Next is the disk read speed is double in case of option 2. Next is network transfer bandwidth is double. All right. So therefore, you can see that it will impact in lot many ways. So I always prefer a decent machine with, say, 16 gigabyte RAM, 16 GB RAM, and multiple of those rather than going for above 16 gigabyte. All right. In case your program is monolith, whereby you cannot break the program onto multiple machines, only then you go for 96 GB RAM. All right. So keep these things in mind. So although everything was equal, ideally, hi, are you able to hear me now?